spherical coordinates now. So my packet of volume, I mean, picture taking a chunk out of, imagine having a Nerf ball. Do they actually still make Nerf balls? But I just haven't seen them in a while. But so imagine a Nerf ball, and you've taken a chunk out of a Nerf ball. So you actually have two arc lengths. This is an arc length, and that is an arc length, and then this is just a straight length. So this arc length is the radius of the sphere times d phi, okay, from the same reasoning here. I mean, your rho is the radius of your sphere, and so if you imagine just kind of emanating out from the origin, your radius of rho, and you move a little bit of angle, then the arc length in that direction is going to be rho d phi, because phi is the angle measured from the z-axis, okay? So phi, you're measuring from positive z, that's your phi. So, you know, picture moving out a certain radius and then moving a little bit of an angle, this arc length then, from the same reasoning of, you know, what you learned in trig class about arc length, is rho d phi. This is here for the same reason that it's up in the definitions of x and y, that if you're trying to, if you're trying to trace x, it's part of the triangle made up, like this would be the hypotenuse of the triangle. And so if we went back through the proof of, you know, how to define x in terms of rotating with this angle and that angle, x is equal to rho sine phi cosine theta, and y is equal to rho sine phi sine theta. So this arc length, you're rotating, imagine, you know, kind of position yourself in the xy plane, and you're rotating in that direction. And so the radius that you're moving is given by rho sine phi, and then the d theta is your little change in angle. So again, this is an arc length in a circle, but the radius of that circle is given by rho sine phi, and then d theta is your little change in angle. And then this side of the box is, I've moved out a certain radius from the origin. If I move out to this radius, I've just made a change of radius. So it's just d rho. So I have two arc lengths, I have two slightly curved sides, and then I have a straight side that is just d rho. And those three things multiplied together make up your packet of volume. So my volume is one of the arc lengths times the other arc length times this straight side. And if you clean that up a little bit, it becomes rho squared times sine phi, and then usually you'll see d rho and then d phi and then d theta. But Fubini's theorem applies here also. We're dealing with continuous differentiable functions, and so the order that you put these does not matter. So just because I'm not in rectangular coordinates doesn't mean Fubini's theorem doesn't hold. I can put those in any order. But usually you're going to end up seeing it d rho and then d phi and then d theta. I think the d rho shows up first because you're always going to have the rho squared in your formula unless there's something, like if you're calculating total mass, and the density had a 1 over rho squared in it to cancel it out. So that's probably why we put d rho first. All right, so for cylindrical and spherical, you do want to go back over these little shapes and make sure you understand what's representing the three sides and how you're multiplying those three sides together to get your volume. If you focus on that, then it becomes less of a having to memorize this versus understanding it. Okay, so if you're setting up volume in spherical, this is your basic triple integral. It's not just d rho d phi d theta, it's rho squared sine phi d rho d phi d theta, because you've had to define your sides differently. Okay, so our first example, we have an ellipsoid, and we are going to set them up. I'm going to first just focus on how to set them up correctly, and then we can pick out some to work out. But I mean, tonight's focus, I want to work on those formulas and make sure people understand how to set up the problems, and you know, then from there, you know, sometimes they're workable by hand, sometimes they're not. Okay, so in rectangular coordinates, my triple integral is just going to be a dz, dx, dy. I want this whole ellipsoid, and because this one's centered at the origin, I could actually calculate the top volume and then multiply that by 2. Be a little careful assuming you can always do this. Again, we're just doing volume right now, so it's perfectly fine for us to imagine the top half of it and multiplying by 2. But if you were calculating mass and the density is not uniform, then don't be careful about jumping to the conclusion that you could use symmetry. Because if your density is not uniform, then you can't assume that the top half is going to have the same total mass as the bottom half. But just doing volume, it's okay for us to do that. And for this problem, I think that would be a good idea for us to set that up. Taking my formula then, z squared is equal to 16 minus 4y squared minus 4x squared. And so z is equal to, the top half would be z equals the square root of 16 minus 4y squared minus 4x squared. So if I calculate the top half, my z goes from 0 to that surface. And then in the XY plane, okay, that's, in terms of interpreting x, I want to picture in the XY plane. So if I'm in the XY plane, z is 0. And so if z is 0, then I need 16 to equal 4y squared plus 4x squared. So 4 will equal y squared plus x squared. Okay, so I'm in the XY plane interpreting how to trace x and y. So if I do dx first, I need to trace this circle. And so x is going to be plus or minus the square root of 4 minus y squared. So again, the only symmetry I'm going to use right now is just imagining finding the top half of the whole ellipsoid and multiplying that by 2. I know you could use some other symmetry here, but I'm not going to do that. Instead, I'm going to recognize that my low limit on x is the back, like this side of the circle, which would be given by negative square root of 4 minus y squared. And then the upper limit is this side of the circle, which is given by positive square root of 4 minus y squared. Okay, so this side of the circle is given by square root of 4 minus y squared, and this side of the circle is given by negative 4 minus y squared. And then what's the radius of this circle? The radius is not 4, it's 2. The radius is 2. So y goes from negative 2 to positive 2. So y is going from negative 2 to positive 2. I'm already tracing the circle by following this formula for low limit on x and this formula for high limit on x.
What would the down be if you weren't doing just half of it? What did you do?
It would be negative.
It would be negative, plus or minus.
Yeah. Yeah, it would be the kind of the same idea here. So if I did not do the 2, this would be negative. Again, for the moment, I just want to set them up correctly, and then we can kind of go look and see if we were going to work them out by hand. I really, looking at this one, if I then took the first z is just going to be this minus 0, and then if you integrate it with respect to x, yeah, so you're gonna have a problem there because you don't have you're gonna have to do a trig substitution because you don't have x on the outside of the square root to be a straightforward chain rule type problem. So it would not be a pretty one to work out, I think. So, but anyway, that is how you'd set it up, and we can type it in Mathematica like that. Should be okay. Okay, cylindrical. We're gonna set it up with cylindrical. I don't wanna, I wanna leave this up here, so, this is the rectangular answer, or how to set it up. I wanna leave it up there though, so I guess don't let it, am I doing that? We're gonna work on cylindrical right now. Okay, so if you remember our little packets of volume for cylindrical, we have R d theta is one side, so R d theta is one side of the packet, and then you have dr and dz. Usually, you see this reordered with R. It really doesn't matter. I know the d theta is usually last. I think in our case, if we did dz and then dr. Well, you know what? I'm going to put dr first and then dz. Okay, so again, the r d theta is the one side, and then you have dr and then dz. So let's look at our shape and shoot, you know what, you guys, I'm sorry, in your notes, you guys, I'm sorry, on your notes, I typed this up kind of quickly, but do you see how I put dz first? but then I put R1 and R2, it should be Z1 and Z2, and then R1 and R2. It really shouldn't matter what order you end up putting them, but through if you're gonna create a nicer interval doing one through the other. If we did DZ first for the one that we're working on, Z is equal to plus or minus the square root of 16 minus 4 times x squared plus y squared. Okay, remember it's 16 minus 4y squared minus 4x squared. So I factored out before. This is equal to r squared. Okay, so in cylindrical coordinates, z is equal to plus or minus the square root of 16 minus 4r squared. I can factor a 4 out of that. And I get plus or minus 2 times the square root of 4 minus r squared. So if I used symmetry, which we can again, I'll put a 2 out here, and z goes from 0 to 2 times the square root of 4 minus r squared. So then I'll integrate with respect to z, I'll plug this in, then I'll integrate with respect to r, and r is going from 0 to 2. Okay, my r is going from 0 out to 2. And theta is making a full turn, a full circle, so 0 to 2 pi is what theta is doing. Okay, theta is rotating around to make a full circle. Now I know it looks like, notice when we were doing the problems in rectangular, I had variables here to trace my curve, I had variables here to trace my curve. It wasn't until the last integral that I put all constants. But the reason why I'm able to put all constants here is because the RD theta is already tracing an arc length. Okay, so the RD theta is already in the packet of volume tracing an arc length for me. So that's why you can just put R 0 to 2 and you don't need to write a formula for R. So in general, it's probably going to be cleaner to set it up with DZ first and then DR. Let me look a minute to see if we did do DR first. You would need to, so that you didn't lose the information about the curve, you actually would need to rewrite R in terms of, put 0 to 2 and then put Z. I don't know, why don't we just leave it that this is the safer way to set it up, okay? Okay, now spherical. If we're going to set it up with spherical, so this was cylindrical, and spherical, our packets of volume are given by rho squared sine phi d rho d phi d theta. Again, the d phi and the d theta can be interchanged. I think, like with this one, I think it's going to be cleaner to set it up if you do d rho first. So we need to do a little prep work. Okay, z is equal to rho cosine phi, and x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And so my formula, I have z, so I have rho cosine phi is equal to the square root, well, plus and minus. So why don't we still kind of think about the top half? So 16 minus 4 y squared, so y is rho sine phi sine theta times minus 4x squared, so x is rho sine phi cosine theta. So then if I factor out the 4 and the rho squared and the sine squared phi, I get, and I'm factoring out the minus, I get sine squared theta plus cosine squared theta, which we know equals 1. And I can factor a 4 out of that, and I get 2 again. So it'll be 4 minus rho squared sine squared. Okay, so that is equal to rho cosine phi is what that equals. So that means that rho is equal to okay, so again that's messier than we want. This is an example where cylindrical legs actually the easiest way to write a Robert, I'm sorry, did you have a question or were you stretching? Okay. All right, so I mean, part of what we're needing to recognize is that you know, you've got to rewrite things in terms of your correct coordinates. And sometimes it's clean and sometimes it's